All right, hello everybody. My name is Korey Pickering. I'm a fourth year undergraduate studying computer science at the University of Texas at Dallas. I'm a CS squared student. My research interests include artificial intelligence and machine learning. And today I am presenting to you a comparative analysis and improved model for test case generation using machine learning. So what is this paper about? Fuzzing is a term given to the process of testing software by mutating a given set of test cases, running a program under test with the mutated input, and monitoring the program under test behavior for crashes and anomalies. Traditional fuzzing programs typically use the genetic algorithm, randomly mutating seed inputs, and using a fitness function based on code coverage to select the fittest specimens for the next generation of test cases. Recent state-of-the-art fuzzing models have leveraged machine learning to improve the efficiency of the fuzzing process. This paper is a comparative analysis of 6 state-of-the-art machine learning-based fuzzing models. The background section gives a brief introduction to traditional fuzzing and discusses the process and its limitations. The models section gives a systemic analysis of each model individually and seeks to answer 3 of our 5 research questions. The improvements section seeks to determine what changes may be made to some of these models to improve their performance. In the future work section, we will outline a research methodology and attempt to design an experiment for building a new machine learning-based fuzzing model capable of outperforming the current state-of-the-art models. The conclusion will summarize 5 research questions designed to aid in the creation of a new machine learning-based fuzzing model. The traditional fuzzing process starts with seed files and a program. Seed files may be given or they may be generated using concolic execution and a constraint solver. The fuzzer runs the program with the given seed input file and collects runtime information, monitoring for crashes and hangs. A mutator function randomly selects bytes in the seed file and performs a random mutation operation. This mutation operation can be anything such as flipping bits, ORing bytes, and etc. A fitness function is usually guided by coverage information. A fitness function usually guided by coverage information filters out test cases that trigger previously unseen edges or rare edges, and these become the set of test cases used for the next iteration of the fuzzing process. Fuzzing programs requires mutating seeds in such a way that program verification is bypassed and code coverage is increased using the mutated test cases. To leverage machine learning, state-of-the-art fuzzers model a stage of the fuzzing process as a classification problem. Seed file generation, test case filtering, mutation operator selection, and exploitability analysis are 5 parts of the fuzzing process that can be modeled as classification problems. So these are my research questions, and they're focused on these 6 state-of-the-art fuzzers. How do these models use machine learning in their process? How do these models compare in their process, advantages, limitations, and performance? Are any of these models orthogonal to each other? What improvements can be made to these models? And how can we design an experiment for creating a new fuzzing model that outperforms these 6 models? The first fuzzer that I studied was called NuFuzz. It's a predictive model trained on binary programs included in the LLaVA-M dataset. Execution paths of the programs are first instrumented to control flow graphs, then represented as vectors and labeled as clean or vulnerable. A neural network is then trained offline to predict if a program path contains a vulnerability. The prediction model is then incorporated into a fuzzing model with process tracing. Seeds are selected and mutated and ran through the fuzzing model. The process trace of each mutated input is then used by the predictive model to predict which paths are likely to contain vulnerabilities. The mutated seeds are then given a priority according to their likelihood that their corresponding trigger paths contain vulnerabilities. The mutated seeds are then put back to the seed pool, and selection from the seed pool uses a priority based on the predictive model. NuFuzz is trained only once offline and then continues training online when incorporated into the fuzzer. After offline training, NuFuzz can be applied to all applications. Experiments in vulnerable code have shown that over half of all bugs are located in less than 10% of the code. This means that code coverage might not be the only good metric by which to judge a test case. Fuzzer is a machine learning-based fuzzing model that is vulnerability guided rather than coverage guided. Fuzzer uses a long, short-term memory neural network to predict the probability of a basic block containing a vulnerability. The input test cases are given a score based on the blocks they trigger and the prior probability of those blocks having a vulnerability. Seeds are then selected according to their score. Fuzzer was found to perform as well at 4 hours as other fuzzers at 24 hours. RL-Fuzz is a policy-based reinforcement learning model that leverages the deep deterministic policy gradient algorithm to select a mutator operation based on test case input. Fuzzing can be modeled as a reinforcement problem by abstracting elements into state, action, and reward. To utilize reinforcement learning, RL-Fuzz uses an actor-critic agent. Mutator functions are the agent's action functions, seeds are the current state, and the reward is based on edge coverage. The critic uses a deep neural network to model the policy and adjust the reward probabilities according to edge coverage information returned by the baseline fuzzer. The actor chooses a mutation function according to the policy. News is a machine learning-based fuzzing model that uses a simple feed-forward neural network to model program behavior based on test case input. The resulting function is then smoothed using convolution to create a differentiable surrogate function. The neural network takes as input a byte sequence as a test case, and the output neurons represent a particular edge. The output neurons compute a 0 or 1 on each input byte, depending on if the byte had an effect on triggering the particular edge that it represents. Input bytes with a higher calculated gradient will have a greater effect on program behavior. The calculated gradient information is used to mutate select bytes. Depending on the sign of the gradient, news mutates and generates test cases by replacing the byte value with all values above or below in the range of 0 to 255. MT-Fuzz is another neural smoothing guided fuzzer created by some of the same people behind news. MT-Fuzz uses a multitask neural network, or MTNN, rather than a simple feed-forward neural network to learn tasks that are related. The primary task of MT-Fuzz is to predict edge coverage based on input. The two auxiliary tasks learned by MT-Fuzz are to predict context sensitivity and approach sensitivity. In all cases, the outputs are vectors representing the edges covered, the call stack, and edges that are siblings of other triggered edges. The reason for the multiple tasks intuitively being that context and approach are also primary factors in triggering previously unseen edges. Like news, MT-Fuzz uses gradient-guided optimization, this time with context sensitivity and approach sensitivity built into the function. Pre-Fuzz is an attempt by another group of researchers to systematically improve upon news and MT-Fuzz, these two being the most state-of-the-art machine learning fuzzers. The paper behind Pre-Fuzz was published on May 21st, 2022. In the original papers, news and MT-Fuzz adopted an edge metric not commonly used by other fuzzing papers. Adopting the common metric, the researchers behind Pre-Fuzz evaluate news and MT-Fuzz against baseline AFL on 28 real-world programs. The results showed that for the most part, news tended to outperform MT-Fuzz, making the case that context sensitivity and approach sensitivity were not as important as simple edge coverage in calculating an input's gradient. The result also showed that the performance of the two were not consistent and could not beat baseline AFL in many cases. Using correlation software, the researchers were able to correlate the results to the size of the programs. AFL Havoc, using random mutation, performed better on smaller programs. Pre-Fuzz was able to perform better using a probabilistic byte selection method based on the gradient scores. So improvements, limitations, and challenges. Out of these 6 models, only 3 have actually been evaluated against each other, and the results were disputable in each case. The creators of Pre-Fuzz found that news and MT-Fuzz did not have consistent results and correlated this to size of program. Random mutations seemed to perform better on smaller programs. They also found that context information added to MT-Fuzz's multitask neural network did not have much impact on code coverage, contrary to the findings in the original paper on MT-Fuzz, although a different measure of edge coverage was used. This highlights another challenge in choosing the metrics of performance when judging these state-of-the-art fuzzers. Different factors are used, such as the number of bugs found, the number of bugs found versus time, and the amount of edges triggered. It is worth considering how much time and resources are wasted by news generating test cases for every value below or above the value depending on the gradient. In this section is proposed a systematic experiment for better understanding fuzzing elements and propose a model using machine learning. The ultimate goal of any fuzzing process is to find more and new bugs. We can start our experiment by finding a numerical weighting to the importance of vulnerability guidance versus code coverage to the number of bugs found. We run baseline SUSR, news, and news with a probabilistic test case selection function based on SUSR's salience score over a set period of time, adjusting the weights of probabilistic news accordingly with only the goal of finding the most bugs. We evaluate baseline SUSR with SUSR bin to vec to see if any performance may be gained from replacing the word to vec model used in the baseline SUSR. Lastly, we introduce a mutation operation policy and evaluate all 6 baseline models versus news with probabilistic test case selection and news with mutation operation policy. To propose a new model, we take into account that the idea behind increasing code coverage is that more code covered leads to more bugs being found. It can be hypothesized that the task of predicting the code coverage of a seed input and its triggering of vulnerability are related tasks. We can model our neural network much like news. In news, the output neurons predict a 0 or 1 depending on if the basic block they represent is triggered. In our model, the input is given a salience score equal to the dot product of the input's predicted block coverage vector and a block vulnerability probability vector. This requires training a neural network such as the one used in SUSR. The predictive model only needs to be trained once. From there, any binary program vectorized from a control flow graph may be used to produce a vector containing probability scores. Gradient-guided optimization is used to pick bytes for mutation probabilistically based on their gradient score, and newly mutated cases whose salience score are above a certain threshold move to the next generation. Test cases that are cold are replaced with randomly mutated test cases with higher salience. That's the end of my presentation. Thank you guys very much.